So next 1 hour, our Professor Tokuro is going to give you a tutorial about the exact TED. So please.
So I think in my tutorial lecture, you already learned about the essence of the backspace media method. So now I will try with the concrete example.
Sound. Sorry, sound is.
Okay, thank you.
Is it audible?
Okay, so first to get my example AD code, so you first access to the workshop website, and you can open the abstract tutorial lectures. Or what is this? Oh, is this a PDF?
Yeah, yeah, you can open it.
Oh, okay.
It was asking for payment.
Double click save this. And thank you. And you can get the link to my AD sample course here. Is this Firefox? No?
Yeah.
No, that is
Google Chrome.
Google Chrome. Okay, I think it's better to use the Firefox. I was told. So, anyway, so you can access to this web page. It's okay, fine. I can copy of this image, and I can. Yes. So, for example, you can see the three Python codes here. For example, I will open the final temperature lattice code, and you can get the copy of this code by, oh, where's the button to copy? I'm not familiar with using the Windows, so can you copy these all? Copy both. And yes, so this is a Google Laboratories web page. So you can access this Google Laboratories page, and you can create new notebook. And to use a notebook, so you need to create a Google account in advance. So that if you didn't have the Google account, so please create first that account. So, and you can paste. And there is a parameter you can tune. So my all lattice-based DD codes are written for the S=1 curve and the J1 J2 spin chains. So the last n means the this is the main subroutine in this final temperature lattice code, and this last n means the number of spins for sites. So J1 is a nearest neighbor interaction between spins, and J2 is the next nearest neighbor interaction. So you need to set the these parameters as you want. For example, if you would like to in system 6 sites spin system, and I set now the J1 equal 1 and J2 equal 0.4, and large L and the large M means the number of some number of samplings or realization for the initial spin configuration, and M is the number of iteration for each launch method. So, for example, R equal 4 and M equal 50, and then so you can run with processing this playable term. So you can run this Python code. So if you don't have the laptop, I think that Google Cloud can be used in your smartphone. So please check if the running is working well. So I'm calling the main subroutine by using the different random seeds for the initial random spin vectors. And there are the three groups are called. And each group will, each main subroutine, main routine will take, now is the full realization for the random spin initial vector. So after computing the expectation value for each main group, so there's three main groups here. So in my Discord, so the standard errors as the statistical error for the final temperature physical quantities, that will be evaluated by the standard error by using these three groups. So in the end, so you can plot now the specific heat and the energy and these temperature dependencies. So if you'd like to extract, for example, how should I copy? Can you help of using the Windows machine? Yeah, how should I copy this line only? Yeah. That will be okay. And we will make a new call cell. By using the press pause button, and you can paste here on this line. And so now I'm plotting the specific heat and temperature dependence with a statistical error. So that's kind of stuff you can do on your laptop or on your smartphone. So what I would like you to do is to reproduce the calculation example 1, 2, 3 graphs that was already shown in my slide. And this slide is also available from the GitHub web page. You can access it from the laptop website. So for example, yes, this one. So this calculation example treats the S equal half anti-ferromagnetic Heisenberg spin chain. And for reproducing these graphs, so you should change the parameter m, and you should also change the J2 interaction value at J2 equals 0. So you don't have to treat the you don't have to treat the same parameter values. I think that you can see how the behavior will be changed with changing the R value and M value by yourself. So please try in many cases, so as you want, and to check the reliability of this final temperature analysis methods by yourself. And calculation 2 example. Yeah, this is for the spin dynamics. So you can calculate the and obtain the spin dynamics for the 1D spin chain by using this simple spin dynamics code. So my Lantus final temperature Lantus code is written by without any symmetry. But for the Lantus methods and continuous fraction spin dynamics methods, codes are written with using the magnetization conservation. So I think the simple final temperature Lantus Python code is the simplest one. So I think, yeah, I can recommend you to read first the inside of this code. Yeah. And now as I said, so my code is written for the J1, J2 spin chain, and the lattice information is defined by this def make lattice chain subroutine. Of course, when you change the inside of this make lattice chains, so you can create any lattice geometry such as J1, J2 square lattice or triangle, Kagome. And that's kind of the stuff I think you can enjoy by using this code. Okay, so that's all my explanations. So if you have any questions, please ask me during the hands-on tutorial time, or you can also ask me later. Yeah. Okay, thank you, and enjoy.
So excuse me, could you show me the specific heat again?
Yes.
So I got something, but I'm not sure if it's correct.
Yeah. Specific heat is this one?
Yeah. I actually got something different. So
Different. Can I see? And that is a specific heat, and that is energy. And I'm just plotting the specific heat result in the next new cell. So if you'd like to plot the specific heat energy only, so that you just type and copy this line. Only one line, okay. So above line is for the energy, temperature, energy. The second one is for the specific. Yes, last one. Yes. Copy and please make the new cell. Yes, and you just type. Yes.
Still different.
Yeah, different, I think. So because I changed the R and the M values by myself, and I think you choose. Let me see the other value. Yeah, you set the value of 10 and M. So I set R equal 4. Yeah. Of course, yeah.
Okay, that's fine.
Yeah, right. So when the number of iteration is decreased, so then the square number will be big.
Yeah.
Sir,
Yes.
please explain the functions what are they doing?
Sorry.
And this explains the binding concept. Yes.
What do you think?
So I think this functions. What are they? Is
No, right. Okay, so slow function. But I forgot to take it, but that is used to make, I think, the next. The next number, I think. Yeah, right, true. Okay. For the snoop function. Okay, so let's go back to the GitHub web page, and you can see the acknowledgement. And yeah, please open this Dr. Kaneko-san's GitHub web page, and there's a web link about the snoop function. Let me look for the snoop. Where is?
You magnify the things a little bit because it's probably hard to see, right?
I see.
Control and trust.
Control bus. Can you see now?
Yeah, it's better.
Yeah. I think there must be the website. Let's see. Uh, we have customer links. Okay, but I think the what you can do by using Snoop, I can show you with using the Snoop function with a concrete example now. Okay. Oops, where is that? Okay, we open the same command to Snoop. Can I copy of these lines? Yeah, can I use a mouse or? Ah. Oh. Yes. Yeah. Oh, sorry. Yes, nice. Thank you very much. Okay. So. Yes. And you can define here the Snoop function. Oops. And get. Yeah, it's much. Let me have time. What I did before, I don't. Yes, no function is used in this make list folder. And now we are thinking about the fixed XG sector. And so the n number of upstream is fixed. And so we are looking for the allowed basis states in this make list function. And should also copy. Okay. So when you have time, yeah, I will answer. It all depends. I'm just looking for another one. Okay, I found a simple explanation about the function. So, the simple explanation is written in the Kaneko-san's GitHub. So the suitable function is used for finding the next higher number after a given number that has the same number of one bits. That's mean the same downspin. So let's see the concrete example. Okay, so to represent given decimal number, for example 10, in the binary representation, you just have to use a bin function. So for example, 10 is described by the 1010 in the decimal in the bit representation. So now Snoop 10 output 12. That means this is the 1101 in the bit representation. So with keeping the same number of downspin, you can find the next spin basis states. That is the function of the Snoop. Does that make sense for you? So the 10 in the decimal representation is equal to the up down basis. That has the total is equal to 0. So we'd like to look for the next spin basis in the total is equal to 0. And that number can be given by the Snoop. And after inputting the previous decimal number in this Snoop function as the argument. Yeah. So this is a function of Snoop. I just opening the line. So if you have questions, please ask me directly. Yes.
Actually, very small.
Small.
If you put one hand minus one, then get one.
One. Yes, next so yeah, okay. And under
Just press. If you put one, then, it seems to be one. Then theory, you get my first one is two. Right? Please, before is two. Or set the second.
So it depends on that. What is substitute for that?
So it's
Okay. Oh, I see, I see. So if you don't take one, then you will get one.
Yeah.
That's that is good.
Yeah.
Just.
Sit. Yeah.
You mean sit in the beach?
Yes. Okay, so each function what is a long size email. So you prefer from the lattice? Okay. So I will ask to explain the kind of flow chart of and in each code and yeah, too many subroutine actually in this ED code. So I will explain briefly the which subroutine is working for what. So actually, so let's start from the main routine. So in the main routine, we are just setting the needed parameters such as the number of spin, and SG means the total SG value, and J1 and J2 are the nearest neighbor and the next nearest neighbor interaction. So, and N up means the number of arc spins, and N here base, and this is the dimension size of the matrix Hamiltonian. So these kind of the parameters can be obtained from calling this init parameters function. So of course, the number of arc spin and the Hilbert space dimension are depending on the system size n and total C value. So in this init parameters is defined here. So by using this init parameters, so you can get the number of arc spin and the Hilbert space dimension size, and these are the needed parameters to do the to make a list 1 and list J and list JB, for example. So making the lookup and the lookup tables.
So,
Yes.
is the Z component of the spin?
Second.
Is the parameter is it?
Yeah.
The Z component of the spin.
Second.
Z component of the spin.
Yes. G component. Total spin. Yes. Yes. G means the G component of the total spin. So that is defined in my lecture notes. Here. That's the definition of the total SG. So after getting these NR and the N-qubit space parameters, and we are setting up the condition to make the lookup and lookup tables. And we are printing out these parameters you set. And this is stuff means that we are evaluating the time to make the to construct the lookup and lookback table. So, and these are the lookup and lookback table, list 1, list JA, and list JB, and that is explained in the part 2 tutorial lecture note. Yeah. Yes, the list JA and the list JB are needed in the ED code. So, and after constructing the list 1 and list JA and list JB, and the next we will define the lattice. So we set the interaction between the spins and JXX and JGG. That correspond to the yes, this one. So this is the XY component of the spin-spin interaction in the component of that. So using anisotropy, if you like to input, and you can change this value in your ED code. And the make lattice chain is defined here. So now you can define here the which sides are connected by the bonds interaction, and you can also define the JXX and JGG values by using these functions. So if you like to add the Ising anisotropy, so you can change here, for example, J1 times delta, for example, then you can add the Ising anisotropy. So after defining the our model Hamiltonian, and now is the time to do the Lanczos procedures. So we set the precision for the convergence of the energy here, and and we set also the maximal number of the Lanczos iteration. I set the 1000 here. So, and this line is the important stuff, I think, to get the eigenvalues and the alpha and the betas. These are the elements of the three-diagonal matrix T. And this is the ground set wave function you can get after calling this simple Lanczos subroutine. So this simple Lanczos function is defined here. So we should construct Lanczos vectors to make first the two-diagonal matrix. So we should set first the random initial vectors as V1 here. So NP random lamp is the for the random generator by using the Emerson twistor, and you can set the random wave vector. So that's V1 is written by, it's defined in my lecture notes, such as the, yes, this is a V1. And I'll to back that out. So, and first we should normalize this initial random spin vector by using this function. And these V0 and W are the space for the another and new Lanczos vectors. So in the Lanczos procedures, we need to create three vectors at the same time, as you learned in the first lecture. Yes, so we are making the VK by using this equation, but you need to store and keep the three vectors at the same time in your ED code. So these are the three vectors, V1 and V0 and W. And we set the initial values. That is the initialization. And pre-energy is for the energy values. And this is the iteration part for the Lanczos procedure. And first, and we should multiply the matrix Hamiltonian to the initial spin vector V1. So that will be done by you calling the Ham-to-Beg subroutine. So by using this Ham-to-Beg subroutine, you can multiply the matrix Hamiltonian. And you can also make the Hamiltonian elements on the fly. So after updating the Hamiltonian to initial random vector, then now is the time to get the alpha value. So the alpha value is obtained from this equation. Now we started from this initial random spin vector. So after operating the Hamiltonian to this initial spin vector, and then so you can get the alpha zero vector by using this equation. So that procedure will be done by using this simple line. And after that, so we should make the next Lanczos vector by using this sentence. So that is now the W is equal now to the multiplication of the Hamiltonian matrix to the initial random vector. So that means the Hamiltonian times V1 is stored in the W function first. So we should subtract the information about the previous vectors. That will be done by subtracting alpha V1 and minus beta V0. Now the beta is now just 0. So what I wrote here is completely the same procedures as I wrote in this page 15 in my lecture notes. So I think you can understand, I think, when you have time. And to do these procedures, you can construct a three-diagonal matrix by using the alpha and the beta coefficients and elements. And you can diagonalize the three-diagonal matrix by using this subroutine, sci-fi routine. So you can get the eigenvalues and the eigenvectors. And here, that is the check of the energy of the eigenenergy of the three-diagonal matrix. So I think we have a question why we divide by 4, and because in the Ham-2-Beck subroutine, and actually, so when you are operating the SIG and SJG operators to a basis, then you can get the 1/4 or -1/4. But I skipped putting the 1/4 here because we should avoid the round off wherever. Yeah, in a sense, so we are dividing by 4 later after doing the Ham-2-Beck subroutines procedures. So, and after getting the eigenvalues and eigenvector from the diagonalizing to diagonal matrix, so you can get the approximate eigenvalues of the original Hamiltonian. So when these minimum eigenvalues, that means lowest eigenvalues, but that is approximated at the moment. And of course, the previous eigenvalues and the current eigenvalues, that difference is very small than this EPS. EPS means that is defined by here as the very small numbers. So that's mean the convergence parameter. So after converging, so that we will stop this lunch procedures by using break. So this is the procedure to get the lowest energy eigenvalues. So after getting the lowest eigenvalues, we would like to construct a ground state eigenvector. So to construct an eigenvector, we should do again the last procedure to realize the eigenvectors of the three-diagonal matrix in the original ST spin basis. So that procedure will be done by using these another and the same and the lattice procedures. So then, and you can get the energy eigenvalues and the corresponding ground state wave function. That is explanation of the simple Lange subroutine. So we are plotting the ground state energy from the ground state and the first and the second and third and fourth excited state energies. At the same time, we are printing. And next is to compute the 2-point correlation function. Sorry, I didn't explain that kind of the function in advance. That's you can also compute the 2-point correlation function by using a calc Z color and the calc X color. But if you already understand the principle of the Ham-2-Beck subroutine here, Ham-2-Beck with, yes, this one. So actually the principle is almost the same to compute the SDSD correlation function or XXX correlation. So you can understand, I think, the meaning of these calc Z color subroutine and the calc X color subroutine. Yes. Yes, that's kind of the stuff, the flow chart and the explanation of this ED large score. Yeah, I think after understanding the meaning of this Lange's score, and it will be easy to understand the spin dynamics sort also, I think. So the almost the same techniques is used. Okay.
Yes.
Yes.
So, what's the meaning of the first line in the harmony of it? W. So you put the W as well.
V1 is okay.
And also you.
W is out. Okay.
So you W but you immediately initialize W.
Yeah. That's for the case. Yeah. I think I don't need initialized by 0, I think. Yeah.
You define the space.
Yeah.
Another question.
Yes.
Is all those can be right?
Yes, and we can parallelize. So for example, so that I was using a photonic digit to parallelize. But I don't know the way for the Python. Yeah, I tried to use the number actually, but I failed. But it is easy to parallelize, I think, by using offline techniques, for example.
So, any questions from the students? No? Any questions?
Any questions from online participants?
It's a simple Python related question. So you have used lists here, but another alternative that could have been NumPy arrays. So is there a reason to just Python list?
Oh, really?
I think it's
I'm coming with the Python solving. Yeah, actually, it's the last time to use the Python.
Not because so it will have a huge mind, little more efficient in lists. So I thought that.
Yeah. Right. I think that is not efficient because I agree. We have the better ideas of this, let me know. I'd like to know. Yeah.
So,
Yes.
so, sit down on it. You always do the calculation.
Yes, about 2%. What do you mean of real space? That's in real space. Yeah, that is science. We should think about whether any convolutional space is so as a can people wins by using this heuristic. And so the list is using the demonstration symmetry. Yeah. So that's the first one is a convolution. Yeah. So as I explained in this graph, so we can use the distinction definition and also at the same time we can also consider symmetry to decompose each blocks into the much more smaller blocks. Yeah. So and each groups are labeled by the value of the vector. So now we are thinking about the
Right now, I don't hold it. So even the code which you are learning now. Here, using the so citing, not that. I mean, not in the case, not in the moment.
So by using the techniques of the work animation with symmetry, so we should construct another basis which are bounded by the vector model. Yeah. Yeah, it's good by this paper. So we should construct the answer file on the same basis to use the transmission. So now let's do the product exploration in the space. Should send out. Oh, I think we also upload a program like this. Yeah, this one. In the basis, which are allowed by
Yes, it's a key.
yeah.
So these,
Yeah, there is a representative basis states that is represent displayed by the up down.
the basis is now
Yeah.
this.
Yes, right. So,
So then if you calculate the energy, that will be in terms of.
yes. So, the energy allowed by the K level. So that's the source of my spider webs. That's K correspond to this level.
Yes. The energy is, if you diagonalize that,
Yeah.
the energy will get it.
Yes. Right. So now we are thinking of a three-dimensional system with the cubic lattice. So the K vector is also the three-dimensional vector. Yeah, K, K.
So now,
I think for the number of downspin is only one. I think you can treat much more sizes. I think
using exact dimension, the maximum system size. What is the maximum?
it's the demonstration. So what you would like to
Let's say it's three-dimensional.
two-dimensional system and let's see.
So, what is the X, Y, and Z maximum you can take? I mean, what is
For example, if the number of downspin is one only, then I think you can treat
without any symmetry?
without symmetry. Without symmetry.
It's very difficult.
Yeah, without symmetry, I think up to the 36 or 40 side clusters, I think we use the supercomputer. I think.
So this, what you are reading here is up to like this.
Yeah.
1,000.
Yes.
1,000 means what? 10 constant.
Yeah, 10 by 10, I think.
So this system size is small, right? So the system size is small. There will be finite size.
Yeah.
How would
We should be careful. Yeah, we should be careful about the finance and scaling us actually. So, yeah, this question, let's say, like this. So,
Like, and of the exact result.
Yeah.
What do you, you
that's quite difficult, I think. Almost impossible. I think we have already demonstrated, yeah. Do some work and meeting. Yeah, of course, yeah. This is my model. Okay. But as I explained in my introduction, I think Amazon Towers analysis is applied to what you can see the time setting down the choice measure rate, like the some aggregates, but we can get information in the final sites. So we need to think about the what's idea is what can we say from the eating this out?
all is exact.
Not all, but for example, this paper, for example, I use exact values method for London Smith system before. And the struggles. Yeah, I guess we did the London is on their basic regularities economy. That's study was considered by some experimental results. And or maybe you can find this type of thing on the archive. So that's what I think. Sorry, so my graphs are heavy always. So I pitched this random passenger model. So in my lecture course, I just treated this Jij as a constant value. So what's in this paper, the Jij depends on the random distribution. So I investigated the static and dynamic features and the dependence of the randomness. So their term is the randomness length. So if there are no randomness case, we can get the sharp beat behavior in the system in the states because we can get the random anti-enable state as well. That's the way it's equation. We can see, yeah, no sharp beat behavior. That's what the randomness induced kind of the disorder of the one state. And we also investigate the dynamic behavior by using dynamic structure partner. And this is also so we can find the growth quantified feature in the strong randomness case. And then the stage content. So as a kind of a spin with the state can exhibit that drawing on the feature, and that could be upstairs as now, which like continue. But another also can exhibit the same similar behaviors. And that's fine. Fine. This good. So this paper was done by yeah, this book is available. Yeah. And you can yeah. We are still developing this book. some. Like,
Yeah,
yeah, it's a good Yes. Yeah, but the problem is like there are many cycles. So now and the next that's next time. So now it's the 5 degrees. That's fine. This is an